Hello, my name is Katharina Wall, and today I will be presenting my ECEC 572 project on resistive memory-based in-memory computing for machine learning. Machine learning has deeply permeated the fabric of modern society. With the rapid rise of machine learning within both hardware and software applications comes a rising demand for greater computational power and data movement. Figure 1 shows the important advances in machine learning and their computational requirements. Current architectures, von Neumann architectures, move data between a physically separated processor and memory, and this can lead to large latencies and power consumption. This is referred to as the von Neumann bottleneck. As a result, in-memory computing architectures are being considered as a promising solution to reduce these accesses to off-chip data, as well as to increase energy efficiency for machine learning algorithms. In addition to this, a large variety of memories are being investigated for their potential within in-memory computing architectures, such as RRAM, SRAM, MRAM, and many others. However, MRAM offers incomparable density and versatility with its innovative circuitry, which has the capability to perform vector matrix multiplication, which I will refer to VMM, and this is done beyond the basic Boolean logic. As such, this presentation will provide an overview of how resistive memory devices and in-memory computing can benefit machine learning and act as a guide for the future advances of in-memory computing. This presentation will flow as follows. First, background information on machine learning's computational demand and its impact on von Neumann and in-memory computing architectures. Next, the basic operation and structural design of RRAM devices will then be covered, followed by examples demonstrating how RRAM devices are used for machine learning purposes. Then, the architectural approaches to in-memory computing is discussed, and the presentation will then end with some of the challenges posed and advances or efforts made to combat them. The world of computing, from chip design to software and systems, has changed dramatically as a result of machine learning. The advances in machine learning, in particular deep learning approaches based on artificial neural networks, improves our abilities to build more accurate systems across a broad range of areas such as computer vision, speech recognition, and language translation. Driven by Moore's law, the computing power of integrated circuits has dramatically increased with denser, faster, and more processing cores in the past several decades. And this momentarily complemented the dramatic surge in computational demands for the increased scale and applicability of machine learning. However, we see that today, the demand for machine learning to tackle larger problems had led to a thirst for additional computational and data movement resources, and further improvements to memory bandwidth, density, and capacity cannot keep up with the scaling of transistors. Therefore, the focus has shifted from device scaling to computer architecture design in an attempt to meet today's machine learning requirements. Modern computing systems adopt von Neumann architecture, which separates the CPU from memory, as seen in Figure 4. During data processing, data is transferred between the CPU and memory via a bus, and as data volume increases, particularly due to data-intensive machine learning applications, high latencies and energy consumption of data transmissions emerge. This phenomenon is referred to as the von Neumann bottleneck, as seen in Figure 5. To overcome the von Neumann bottleneck, in-memory computing fuses memory modules and data processing units together, as seen in Figure 6. This reduces frequent data transportation between memory and data processing units in modern computers. In addition to this, the non-volatile memories, in particular RRAMs, which stands for resistive random access memories, these are employed within most in-memory computing architectures to further eliminate and reduce data movements between the non-volatile memory and main memory during the power on phase. RRAM, which stands for resistive random access memory, is a non-volatile resistive memory. A resistive memory generally represents a two-terminal device whose resistance value can be programmed by applying an external voltage or current. RRAM can be categorized into two main categories: analog RRAM and binary RRAM. RRAM technology advances for its high data storage density, as well as the compatibility with CMOS technology. RRAM devices enable logic in memory to perform stateful logic operations. By combining complex logics such as vector matrix multiplication, which is used to represent synapses in neural networks, with RRAM, a fast energy computer is created which can execute heavy logical workload. The RRAM stores binary inputs as resistance or conductances before performing computation. And to allow in-memory computation, voltage is applied to these resistances. The output current represents the logic operation result. Figure 8 shows the use of a RRAM array for performing dot product computation. Each bit line connects to each word line through a RRAM cell. Let G denote the conductance matrix, where conductance is 1 over R, and V will denote the voltage matrix. On applying the voltages to the conductance of each cell, a current passes from the cell into a bit line. The total current then will be the sum of the currents flowing through each column. Therefore, the total current is the dot product of input voltages at each row and cell conductances in a column. In neural networks, the synaptic weights of neurons are encoded as conductances of the RRAM cells. Then the total current of the output of the neurons are then the currents. RRAM arrays can be used to implement the DNN inference function very efficiently. Inference in machine learning is a stage where the trained model is used to infer or predict testing samples. Neural network models typically contain many layers of matrices, and each of these can be deployed on one or multiple RRAM arrays via 3D stacking. The similar voltage current flow mechanism of the VMM vector matrix multiplication is used to represent synapses where the resistances are the synaptic weights. As a result, our RRAM arrays are used in various neural network models with the assist of weight segmentation techniques. For these models, the input vector and the feedback of the output vector are encoded in voltage format and then fed into the RRAM arrays in parallel. The intermediate computation results come from different columns of the RRAM array simultaneously and therefore this sort of parallel execution can dramatically improve the throughputs. RM devices can efficiently mimic biological neuron functions. A single RM device contains a resistive layer by 2 electrodes. During programming, set operations increases the device conductance, whereas a reset operation decreases its conductance. This process is accompanied by a delay, which can be controlled through carefully selecting an external shunt capacitor. This delay is the key feature to mimicking the threshold firing operation in spiky neurons. This is where only inputs larger than a certain neuron threshold leads to output spikes. The threshold firing of RM behaves in a similar way as an ion channel formation in biological neuron cell membranes. Neural network model sizes surge as deep learning methodologies prevail in solving the recognition and regression problem. How to implement large-scale in-memory computing systems are very important. For RM-based large-scale systems, the circuitry together with the RM often dominate the overall power, chip area, and energy consumption. This section of the presentation therefore will present both in-memory computing macro designs with different convergent interface circuits and macro architectures of RM based in-memory computing. An in-memory computing macro is the basic processing core of VMM operations. RM-based in-memory computing operates in an analog format and therefore requires data conversion for the macro to interface with its surrounding digital systems. Analog to digital and digital to analog converters are used to bridge this gap. The digital input vectors are converted into cues of analog voltages. And as well as the conductances, and then the dot product engine performs the VMM computation. The output current is converted to a digital output vector by the ADC. Digital approaches can simplify the data conversion inside the in-memory computing macro. To digitalize the input vectors, a multi-bit digital input is applied to the RM array bit by bit. In this way, digital to analog converters at the input terminal are removed, which usually consumes much more area. However, this is being done at the cost of increasing the computing cycles. The quantization of the conductances lowers the output precision requirement of up to 4 bits, which will simplify the ADC design. Instead of conventional ADC architectures, low precision ADCs are feasible from multiple binary sensing amplifiers. And such a simplified design scheme without an ADC module reduces the area and power consumption, but this introduces increased latency and operation overhead. Motivated by the limitation of level sense amplifier-based design in voltage representation of data, spikes are used to represent the data. During computation, the RRAM array performs vector matrix multiplication, and the circuit converts the output current to spikes. In this in-memory computing macro, the activation function computation is executed on the fly, and this will eliminate the need for additional gates or circuits to calculate activation function, and this will reduce design overhead. The spike-based design enhances the energy efficiency by lowering the power consumption at the cost of latency overhead. Instead of using multiple sensing amplifiers, the circuit performs data conversion by continuously charging and discharging a capacitor, which requires 10 transistors and a capacitor. So due to this small requirement, more circuits can be included, leading to a higher execution parallelism and bigger throughput. Microarchitecture focuses on the effective control to utilize in-memory computing macros. Figure 4 shows a RRAM-based CNN in-memory architecture. It is organized in a hierarchy of chips and tiles. The on-chip network bridges the tiles within the chip for data transmission. With each tile, EDRAMs buffers are used for storing the result aggregations. In-memory architectures are composed of a group of RRAM arrays together with a data conversion interface, and then they conduct the VMM, and the output registers store the aggregated results. Additionally to this, digital components perform the pooling and activation operations in neural networks. This particular architecture being shown uses the ADC macro design. Operation in the analog domain brings several challenges such as noise and non-zero wire resistance. Additionally, storing intermediate analog output and implementing max pooling in the analog domain is challenging. Further on, using analog circuitry communication with the digital circuit requirements with the use of ADCs and DACs. These can reduce the signal precision and incur area and energy overheads. The high defect rate leads to reliability issues. For example, due to single bit failure, a cell can get stuck at high or low conductance value. And with increasing device failure rate, the accuracy of neural network reduces drastically. To mitigate this issue, redundancy-based techniques can be used, however, they can incur complexity and error overheads. RRAM has high write energy and latency compared to other memory devices, which increases the overall power consumption. During neural network training, precise tuning of RRAM requires frequent update of weights and large number of training iterations for convergence. And this leads to a large number of writes and a large energy consumption. Lastly, not all neural networks or layers can be implemented using RRAM. For instance, LRN layers cannot be accelerated with crossbars. A 2-bit per cell RRAM based in-memory computing prototype in 90 nanometers CMOS has been proposed for area and energy efficiency of DNN interface. An input splitting scheme replaced the power-hungry ADCs with simple SAs. 3 different DNNs were benchmarked, achieving accuracy of 87% and energy savings of at 1.2 voltage supply. And an 8-bit RAM based in-memory computing architecture was also proposed to, which is based on novel mapping method that can maximize weight and input data reuse. NeuroSim was used to estimate the area and latency and energy, which showed at least 65% savings of latency and energy in interconnect and buffers. And this novel mapping and data flow achieve overall 2 times speed up and approximately 17% improvement in energy conservation. In conclusion, our RAM based in memory computing architectures reduces latency and power consumption compared to that of traditional von Neumann architectures. Our RAM based in memory computing architectures has revolutionized the field of machine learning in that it is able to meet the computational and data movement needs. However, our RAM poses accuracy, area, and power consumption overhead challenges within in-memory computing for machine learning. And this concludes my presentation. Thank you very much.